Hi folks, we are back, section 4.1.5, talking about the relation between Fisher's linear discriminant and least squares. So previous sections we've covered treating our classification problem as regression, and then using our least squares tools to find the discriminant projection basically. And we saw that that works, but it kind of can be a bit problematic. And then we looked at Fisher's approach, which was kind of a sort of a dimensionality reduction approach, which is saying let's try to find a projection that keeps the two classes tight within themselves and kind of far apart. And we found that we found his discriminant that way. And now what we're going to do in this particular section is to show that there is a connection between these two. That in fact Fisher's linear discriminant in the 2D case is gonna correspond to doing least squares with a particular encoding of the class labels. Now the section itself is going to be actually it's short and it's just computation that we do, and I can't give you too much intuition for what the connection will end up being. All I can tell you is that that there should be a connection. We might be able to guess that from thinking about what least squares does, right? And in the least squares setting, you can imagine that if we have the correct class labels, well, then we want those classes to be quite tight, right? Because we're saying that conditioned. Imagine, remember that in the regression situation that we're applying here, our class conditional distributions are Gaussians around whatever the class label is. So ideally, like you want to have that projection be quite tight. Let's say the projections that we're predicting to be in the class that's labeled 1, we want them to all project to a value that's very close to 1. We don't want them to be like projecting to like plus 0.5, 1.5 and 0.5. That's like noise around the ideal value. So we want the classes to be tight around their target basically. So that's one part, and that is reminiscent of what we do in Fisher's linear discriminant, where we want the classes to be tight, the within class variance to be small, and then the between class variance you want to be large because, well, that's what's allowing you to label one group as +1 and the other group as 0, right? So if the between class variance was low, then that just means that the two classes are lying on top of each other, which means you're not really doing a classification. So in that sense, you're kind of messing up your least squares criterion as well, because some of the values that you should be assigning to 1, well, they're getting all mixed up and they're kind of hanging out around 0. So I think that's just trying to give you a little bit of intuition about why these two might be related and why you might kind of go about trying to find the particular relationship. But as for the actual relation that comes up, I don't have any good intuition for it, so I don't want to say any more about that. If any of you guys have a good intuition, please just post in the comments and we can all learn from that. Okay, so let's just get on with the section. I think it's pretty short, and yeah, let's just do it. Okay, so the relation to least squares. Okay, so the least squares approach to the determination of a linear discriminant was based on the goal of making the model prediction as close as possible to a set of target values, right? We just talked about that. By contrast, the Fisher criterion was derived by requiring maximum class separation in the output space. Okay, so like, a priori, it's like the connection between these things is not necessarily clear. And it's interesting to see the relationship between these two approaches. In particular, we shall show that for the two-class problem that we've been covering so far, the Fisher criterion can be obtained as a special case of least squares. Okay, so that's kind of what we're going to be doing. Great. Okay. Okay, and so the question is, why would you go and look for such a connection? But maybe, so, what I've told you so far would kind of motivate that. Okay, so far we have considered one of k coding for the target values. So remember that was a one hot thing, right? Binary, 1 for the correct class and 0 everywhere else. If, however, we adopt a slightly different target coding scheme, so that's going to be important, then the least square solution for the weights becomes equivalent to the Fisher solution. Okay. In particular, we shall take the targets for class C1 to be n over n1, where n1 is the number of patterns in class C1, and n is the total number of patterns. So this is, and the key thing is, so let's kind of highlight a few things. So the targets for class to be this, this target value approximates the reciprocal of the prior probability, right? So the prior probability will be n1 over n, and we're taking it to be the inverse of that. And the only other thing is we do the same thing for the other class, but we've actually got a negative label on it. Okay, so let's just highlight a few things. So this is a negative reciprocal of the prior probability, etc. Okay, so now we're going to look at the least squares criterion. So with our new labels, right? So now instead of having a one hot thing, we just have these plus n over n1 and minus n over n2. And that's going to be determined by the true labels. Okay. So the sum of squares error function can be written as this, right? So we're finding a projection of the point. There's going to be some bias term and then subtracting out the true value. Okay, so then we just do the normal thing. We set the derivatives of e with respect to w naught and w to 0, and we obtain, so this is so far is just very standard. Then from 4.32, so this is this condition, and making use of our choice of target coding scheme, so that's where this comes in, we obtain an expression for the bias of the form so you're just going to be projecting your weights onto the mean, the global mean, where we have used that the sum of the labels actually sums to 0. So essentially our labels are balanced. You weighted them and given them the right sign so that they add up to 0. And m is the mean, so exactly what you would expect. And then you just do some algebra, which we can work out in exercise 4.6. The second equation, so this one, the equation for w ends up being related to the within class variance that we computed before, the between class variance, and it's going to be proportional to the difference in the class means. And then just like before, using 4 point, we note that this product here is always in the direction of the interclass mean vector. And so w is going to be always proportional to the inverse of the within class variance times the difference of the class mean. So this is exactly what we had before. Thus the weight vector coincides with that found from the Fisher criterion. Okay, so that's the main thing. In addition, and we get this kind of intuitive result, we have also found an expression for the bias value. This tells us that a new vector should be classified as belonging to class C1 if you subtract out the mean. So if you center your data, if the projection on the center data is positive, otherwise it's in the other class. So basically that's the end of the section, and the trick was to relabel our data and essentially balance the data sets so that the least square solution matched the Fisher's solution. So in some sense, it also says that Fisher's approach doesn't avoid the problems that we saw with least squares necessarily, right? Like remember we had the sensitivity to the outliers. That's still going to be there, right? Because essentially all we've done is we just changed our labels, and the location of those points isn't going to be really determined by, isn't going to be affected by this change of the labeling. So those issues that we saw with least squares, we would expect to see them here as well, in Fisher's approach as well, because ultimately there's kind of a squared error criterion being optimized in the two. Okay, so a very short section here. I couldn't give you, I think, much more intuition than the section had. The section doesn't have very much itself. But if you guys have additional intuition and insights you can give us, please let the rest of us know in the comments. We'd be happy to read those. And next time we will pick up with Fisher's discriminant for multiple classes. So I hope to see you then. Bye.